We've now seen how to take triple integrals and how to define triple integrals in Cartesian coordinates and in cylindrical coordinates. And these were a little more familiar to us, these coordinate systems, because we're so comfortable with rectangular coordinates and polar coordinates in the two-dimensional setting. And we've been working with these for a while now. The last coordinate system that we are going to introduce and talk about triple integrals in is spherical coordinates. And this may seem a little foreign to us at first. So let's define spherical coordinates and see some examples of curves in spherical coordinates so we have an idea of what this coordinate system is doing and what certain functions in this coordinate system look like. So let's draw our standard X, Y, and Z coordinate system. And we have a point P up here, and that we've usually described as X units away, Y units away, and Z units away from the origin, right? Well, now we want to keep spheres in mind because we're looking in spherical coordinates. And so we can now describe this point in a completely new manner. We can look at the linear distance from the origin to this point P, and this distance we're going to call rho. This is the Greek letter rho. Maybe you've seen this before to indicate density. So this is the Greek letter rho. We also have, if you think of this point as being projected either above or below the XY plane, well, then again, this has some angle theta from the positive x-axis, right? And so we have theta, which we're very familiar with, the Greek letter theta. And lastly, the last variable in spherical coordinates is this angle down from the z-axis. So if you think about the z-axis as just a pole sticking straight up, well, then if you go down from this pole in any possible direction, it makes some angle, right? And this angle we call phi, the Greek letter phi. Here. And now we can represent this point in spherical coordinates of rho, theta, and phi. And let's write what these are doing. So rho, or here, whoops, let me quickly sketch this again. We have a point, we have rho, we have theta, and we have the angle phi down from the positive z-axis. Now, rho is the distance from the origin. And so because of that, rho is some non-negative number, right? If you're at the origin, rho is 0. We have theta, which is the angle between the positive x-axis and the projection of rho onto the xy plane. And so you can see here what I'm talking about is like if this line here is some radius rho, well, if we look at its its vertical projection into the xy plane, we get just this line here, right? And the angle theta is still the angle theta that we were thinking about in cylindrical coordinates even. It's just the angle between the positive x-axis and this projection. And then, so because of that, you know, theta sweeps around the entire xy plane. And so because of that, theta is between 0 and 2 pi. And now what about phi? Phi is the angle between the positive z-axis and rho, right? And again, so how to picture the angle phi is you have a pole sticking straight up that represents our z-axis. And the angle between some line and this positive z-axis is the angle phi. And because this is in any possible direction, the absolute biggest angle you could have is pi. Because if you go past pi, right, say I'm coming down on the left or on the right, and I hit pi. Well, once I go back up, then this makes an angle between 0 and pi on the other side, quote unquote. There's not really sides here since we're in a 360-degree setting. But so then, because of this, phi is between 0 and pi. The biggest angle that phi can be is pi. And let's look at some like examples of phi, because this is kind of, in the past, a lot of students have struggled with understanding this concept. And so if we have, let's look at just the positive z-axis here, and then we have the xy plane. So we have the xy plane, and then we have the positive z-axis. What is the angle phi equals 0? Well, the angle phi equals 0, let's write this down here. The angle phi equals 0, that's the positive z-axis, right? Because we're at no angle from the positive z-axis. So this is the positive z-axis. What about the angle phi equals, let's say, pi over 4? The angle phi equals pi over 4 is going to be a 45-degree angle down from the positive z-axis. But this is in every possible direction. And so that's a cone. If you can imagine taking a line that has a 45-degree angle to the positive z-axis, if you took this line in every possible direction around this, you get, it sweeps out a cone, right? And so this is a cone. And in fact, if you went phi is pi over 3, this would be still a cone, but at an angle of pi over 3, so it would be a little bit wider, like this. And now you can see how phi kind of sweeps in like a conic manner here, and you get these cones. And so if phi, what do we get when phi is pi over 2, though? When phi equals pi over 2, this is the xy plane. Because pi over 2 is a 90-degree angle, and so you're getting all lines that are perpendicular to the positive z-axis. Well, you can see that that would be the xy plane. And then so if phi equals things like 3 pi over 4, right? Well, then you get a cone that's now opening downward. So if phi is at like 3 pi over 4, or say between pi over 2 and 3 pi over 4, you know, you're getting these cones that open downward. So this is a downward opening cone. And then so what about phi equals pi? Phi equals pi is once you're all the way down to pi, this is the negative z-axis. And so hopefully this helps you picture what phi is doing and why it can only be between 0 and pi, is because each phi, every value of phi gives you a cone, right, at where the sides are at whatever specified angle phi has given you. And the biggest you could go is once you get to pi over 2, you're at the xy plane. And then after pi over 2, you have these downward opening cones. And then they kind of close back up into phi equals pi, which is the negative z-axis. Okay, so that's helpful, hopefully, so we can understand what this variable is doing. And now we have some conversion formulas for spherical coordinates. If we want to go from spherical to rectangular, well, we have the following conversion formulas. X equals rho cosine theta sine phi. Y equals rho sine theta sine phi. And Z equals rho cosine phi. And we also have formulas to go from rectangular to spherical. And so these aren't very difficult to derive. You just need to think about the geometry and the trig of what's going on here a little bit, and see if you can derive these formulas. For rectangular, we have rho squared equals x squared plus y squared plus z squared. And so it's like a one dimension higher analog of the radius that we've been talking about in cylindrical coordinates, and polar coordinates, I mean. We still have that tangent of theta is y over x, right? Because theta hasn't changed in spherical coordinates. It's still the same theta. And then we have that phi is arc cosine of z over x squared plus y squared plus z squared. And so we'll use these to go back and forth between spherical and rectangular coordinates. There are conversion formulas between spherical and cylindrical and vice versa. So remark, we can define conversions between cylindrical and spherical using our notions that like x squared plus y squared equals r squared, tangent of theta equals y over x, and z equals z, right? And so, there's not much to it, but you can use these, and it can bode useful to think about conversions between spherical and cylindrical coordinates. Okay, so hopefully this gives us a good idea of what spherical coordinates are doing, right? Now let's define integration in spherical coordinates. So now what does a spherical box look like? Because once again, we're going to take a box, we're going to partition it, and then we're going to find approximate volume and then take limits like we've been doing, right? So now we have a change in theta, which looks something like this. We have a change in phi, which looks something like this. And then we have a change in rho, which is this. And so basically, the best way to picture this is like imagine, so this isn't the best picture here. Let me see if I can redo this. Imagine you took like a basketball or any sort of ball and thickened it a little bit. And then you cut out a chunk out of this thickened basketball. And this chunk is going to be what this spherical box looks like. So here, maybe you can picture this a little better. And now we want to find the volume of this box. And so let's say we have rho is between A and B, right? And so there's like changing like the inner sphere, or the chunk of the inner sphere is at rho equals A, and then the chunk of the outer sphere is at rho equals B. We have theta is between alpha and beta, and that's these angles, right? So we have alpha here, and then we have beta here. So let's say theta equals, and theta equals. And then we also have our change in phi. which is something between, let's say phi goes between gamma and psi here. So we start at phi equals gamma, and then we go down like it's an angle down then to phi equals psi. Okay, that's not a very good psi. And if you're not familiar, right, this is the Greek letter gamma, and this is the Greek letter psi. Okay, and so now we want to partition all of these. So let's partition, right, because we want to find the volume of this spherical box, right? And so we're going to partition AB. Let's partition this into L subintervals. Let's partition alpha beta into M subintervals. And then let's partition gamma psi into N subintervals. Right? And so the ith, or the ij kth box here. So remember, like, what are these partitions doing? Well, this is the row partition here where we're getting like different, we're chopping up the increments of our radius. We also are chopping up the increments of phi, which looks like this here, or of theta rather, sorry, which looks like this. We're chopping up the theta interval into smaller increments. And then we're also chopping up the phi into smaller increments, and which, so it's kind of hard to picture here, but then we get the ij kth box, right? Like somewhere in here, we have bij k, and we want the volume of this ij kth box, right? Which we'll call delta V is going to be something. And so let's picture now the ij kth box here. So we have something like, well, okay, let me just redraw how I was. Right, okay, and we have this like chunk out of a sphere kind of again. And the ij kth box here, which we'll call bij is between, so between row values, row I minus 1 out to row I. And so our row interval, this length, or the interval, is row I minus 1 to row I of length delta rho. Okay. Then we also need the change in phi here, right? These are rounded. Or let me use a different color here. We're going from phi k minus 1 to phi k here. So here is phi k minus 1, down here is phi k, right? Because that's like the change in this angle here of length. Now, what's the length of this, right? This is actually curved. And so we need to use this fact that this is rho times the angle here. And what is this angle? Well, this angle is the change in phi. And so this curve, the length of this curved piece here is the radius times the angle that we've taken. And so that's rho delta phi. And the last thing we need is this change between, so this is going to be the interval theta j minus 1 to theta j, right, where theta j minus 1 is this angle here, and theta j is this angle here, right? And now we want this change, which is also curved, right? And because it's also curved, well, what is this curve here, right? Well, the curve, so of length, well, the change in angle here is delta theta. So we know we'll have a delta theta, and then it's times whatever the radius is here. But the radius isn't exactly rho, right? This is the projection of rho. And because it's the projection of rho, right? So rho is like out up here somewhere. And if you look at this projection, you'll see that this distance here is actually rho sine phi, right? Just set up the triangle with, you know what your angle phi is. That angle phi there is the same as this interior angle here. So this is also phi. And then if you look at this, the hypotenuse being rho in here, right? So what do we have? We have this triangle here. We have rho here. We have that this is phi, and so therefore this is phi, right? But we want the length of this angle here. Well, then if this is phi and the hypotenuse is rho, this is rho sine phi. And because of that, this distance is rho sine phi, and then that makes the length here rho sine phi delta theta. Therefore, we can set up that dv is equal to, well, it's the product of all the lengths that we calculated, right? It's delta rho times rho delta phi times rho sine phi delta theta. This gives us the volume of the ijkth box. And then remember, what is the integral doing? Well, we have some fourth spatial dimension w. We're looking at how the surface, or how the hypersurface behaves over this box. And we take the volume of the box times this height to get the volume of the four-dimensional solid. And therefore, this volume that we're trying to calculate is approximately the height here. But what is this height, right? Well, we need our sample points again. So we have some sample point in every sub-box, and we look at the value of the function over those sample points. That gets us the heights to calculate our approximate volume. And so we need, in each of these, we need a sample point. So I'll say sample point or test point of rho ijk star, theta ijk star, and phi ijk star. This is our sample point. And so the height is going to be f of the sample point, right? And so then we're taking the triple sum. I goes from 1 to L, J goes from 1 to M, K goes from 1 to N of, so F of rho ijk star, theta ijk star, phi, that's rho, phi ijk star times delta V, right? Where delta V was this quantity here. And so that means the volume is exactly the limit as L, M, and N all approach infinity of this triple sum. I goes from 1 to L, j goes from 1 to m, k goes from 1 to n of f of our test point, or the sum over f of all of our test points, ijk star phi ijk k star delta v. And so now we have a definition, and this is the triple integral over this region, or over this spherical box B, of f of rho theta phi dv. And what does Fubini's theorem tell us? Right, we have Fubini's theorem, which says that this triple integral may be expressed as an iterated integral. This is the same as the iterated triple integral, where rho goes from a to b, theta goes from alpha to beta, and phi goes from gamma to psi of f of rho theta phi. And now what was dv? Well, delta v, let's simplify what delta v was. Whoops. Here we can see delta v is equal to, well, we have a rho squared sine phi, and then delta rho, delta theta, delta phi, right? And this was what we came up with to calculate the volume of these sub-boxes. And so because of that, dv is equal to rho squared sine phi d rho d theta d phi, right? And so this is rho squared sine phi. I'm running out of room, so I'll write the differentials below. So d rho d theta d phi. Okay. And so again, remember, this is dx, dy, dz, which was r dr d theta dz here. And so when you express an integral in spherical coordinates, or if you convert from one of these, between any of these coordinate systems, you have to convert the differential properly, right? So here, we have to tag along this rho squared sine phi with our differentials d theta, d rho, d theta, d phi, right? And so again, by Fubini's theorem, there are 6 possible orders of integration here, and I'll just write them for the sake of completeness. We can do what's listed above, d rho, d theta, d phi. We could do d rho, d phi, d theta. We could do d theta, d rho, d phi. We could do d theta, d phi, d rho. We could do d phi, d rho, d theta. And then lastly, we could do d phi, d theta, d rho. Okay, and so again, by Fubini's theorem, there are 6 ways that we can interchange the order of integration, and they're all completely valid. So this is going to end the first video for spherical coordinates. Again, spherical coordinates are a little more foreign to us at this step. So I'm hopeful that watching through this video will, after some time, we'll get comfortable with spherical coordinates and also how we defined the integral in spherical coordinates. And in the next video, what I'll do is very similar to what I did for the cylindrical coordinates videos, is I will spend the entire next video using examples to help us gain a better understanding of integration in spherical coordinates.